Now let's see a small demo in MATLAB where we have simulated all the signals that we have seen earlier and all the properties of it and how the manipulation of the signal affects those properties. Okay. The first is the set of standard signals that we have seen before. Okay. So here what we have is the step function, the rectangular function and the sinusoid. Okay. So if we run these, we should be able to visualize the step function and the rectangular function and the sinusoidal function. So the first plot here is that of a step function. So the unit step function, remember it starts at time t equal to 0, and for the negative values of time it stays at 0, and for the positive values of time it's just 1. And the first plot here just shows what is the plot of the unit step function. And the second plot is the rectangular function. Remember we said that it is non-zero only between minus half to plus half, and it is 0 everywhere else, and that's exactly what we have. So this is the rectangular function when you plot it. And the next plot shows the Dirac delta function at exactly time t equal to 0. It just keeps going on up until infinity, but when you integrate it, the area will be 0. Everywhere else, the value of the function is 0. And the final plot is a real valued sinusoid. It has the cosine and sine, as you can see in this plot. The cosine function is the blue one, which at time t equal to 0 has value 1, and the sine function is out of phase with the cosine function by pi by 2 radians or 90 degrees. So the one that we have here has a period which is equal to the period of this function, as you can see from this plot, is actually pi. So it should be 3.1415 and so on. So the frequency here is, the angular frequency here is in fact given by 2, and if the angular frequency is 2, then we know that the period is given by 2 pi by the time period t. Okay. So or the time period is given by 2 pi by angular frequency, and hence the time period turns out to be pi, which is 3.1415 and so on. So you can see where the signal starts and completes one complete cycle. So it probably starts at, let's say, 0, and in order to see it completing one full cycle, then you have to extend the plot beyond 2. So let's say we observe it from somewhere close to minus 1.5. Then as you can see, the same value is attained somewhere after 1.5. Okay. So which means that the period is roughly equal to pi. So you can change this. So this MATLAB file is given to you. So you can look at this, play with it, change the values, change the functions, and then see what happens. Let's, for example, let's try and change the frequency here. Let's change the frequency to pi and let's see what happens. So now frequency has changed, which means the period has also changed. Now the frequency is pi, roughly about pi. So as you can see, the period has now changed to 2. From minus 1 to 1, you can see a complete cycle, right? Now if the period is 2, what is the angular frequency? 2 pi by 2, which is pi, which is exactly what we have said. Okay. So you can keep changing this and then see what happens. So these are the standard signals that we saw in our discussion, and the plots of them are given here. You can extend the time. So the plot is between minus 2 to plus 2. You can change it. You can change it to whatever time interval that you want and observe what happens here. Okay. And the next thing that we will see is time shifting and scaling. So what if we shift and scale these different signals? Let's start with the step function. Okay. So the dotted red one here is the original step function, and the blue one is the shifted and scaled version. So what is the shift and scale values? The shift parameter here is b, which is given by 1, and the scale parameter is here given by 2. So the signal here is u of 2t plus 1. That's what is plotted here. Ignore these legends now. So it gives the energy, but of course we know that the step function has infinite energy. However, when you plot, you are plotting it between only -2 to +2, which is a finite time duration. So the energy computed there is for this finite time duration. Of course, that is not really true for signals that are extending from -infinity to +infinity. Step function has infinite energy. So the energy here is not really the energy of the step function. Now let's see if we change the shift to something negative, what happens? Right now, once again, the dotted red is the original signal and the blue is the shifted and scaled. Now we'll change the scale parameter to negative and see what happens. So as you can see here, now the scale parameter is -2 and the shift parameter is still 1. Now the graph is 1 for the negative values of time and it starts becoming 0 at 0.5. Till that point it is 1 and after that it is non-zero. Basically this is time reversal and shifting. Now let us change this to -1 plus 2. Okay, now the graph has gone out of range because we are plotting only between -2 to +2. Let us see if it is 1.5. Now the scale parameter is -1, which means there is a time reversal, and the shift parameter is 1.5, which means you have time reversed it and then shifted by 1.5. Now let us say that there is no time reversal or there is no time scaling. So we are shifting it by 1.5 plus 1.5, so the signal has moved to the left. Okay, what if it was minus? As you can see, the signal has moved to the right. Okay. Now we can do the same things with other signals, the rectangular signal and the cosine signal. So as you can see, the original signal is here, the dotted red, and the manipulated or the shifted scaled version is here. Once again, for the cosine signal, ignore the energy here, it is infinite, but for the rectangular we can see what happens. Okay, so this is the rectangular signal, this has finite energy, so the energy that is computed here reflects the actual energy. So we can see what happens when we are shifting it. So when you are shifting it to the right, the energy remains the same. When you are shifting it to the left, the energy still remains the same. But what if we are scaling it? Let us say we scale it in time by 2. Now the energy has become half. So remember, this is one of the properties that we saw. The signal got compressed, which means the content that is present in the signal has reduced and hence the energy has reduced. Now let us set the scale to 0.5, which means now it will expand. Now the signal has expanded, which means the content in the signal has increased, so the energy has also now increased. Okay. Now let us see for our regular, this is the standard function which we keep using, which is asymmetric, right? Now this is the original signal, dotted red, and the time scaled and shifted version is there in blue. As you can see there, the original energy has been increased in the time scaled version because the content in the signal itself has changed. Okay. So this confirms whatever we saw earlier about energy being different when you time scale it. Okay. Time shifting does not affect it. We can see that here. Let us say we just set the scaling parameter to just 1 and simply shift it by, let us say, 0.5 or 0.2. Now there is a shift, but the energy remains the same. Okay, the energy is computed just by computing the area. So that is how you compute energy here, area under the squared value of the signal. So once again, you can create your own signal here, plot it, shift it, scale it, and then see what happens. Okay. The other important signal that we saw was the phasor. So let us see a complex sinusoid as a phasor. So as you can see here, we have multiple plots. So what is the first plot that we have here? This is the real part of the phasor, and whatever here on this side is the imaginary part, and whatever is there, the radial plot or the polar plot is the actual phasor plot. So, it shows the rotating phasor, and the magnitude here is the magnitude plot. The bottom left is the magnitude plot and the bottom right is the phase plot. Remember, we talked about the phase wrapping. That is exactly what we observe here. The phase is only between minus pi to plus pi. Phase keeps wrapping because when you compute tan inverse of something, you will get a value only between minus pi to plus pi. Even though the phase can be any value beyond pi, the computation gives us something only between minus pi to plus pi. So, you keep getting a phase which looks like this. Let us replay this and see. So, we have set a particular frequency. The frequency here is set to be 7 radians per second. That is our angular frequency, and the magnitude is set to be 1. Okay. And that is what we observe here. So, this, as you can see, the frequency is positive, which means the phasor should be rotating in the anti-clockwise direction, and that is exactly what we are seeing here. And the real part is nothing but cos omega t, A cos omega t or R cos omega t. The R is 1, so you see an amplitude of plus 1 to minus 1. And the imaginary part is R sin omega t, and that is exactly what we are seeing here also. The magnitude is always 1, so you just see a straight line, and the phase just keeps increasing, and that gets wrapped around when you plot. Now, let us see a negative phasor. So, what if we change this to minus 2, let us say. Now, you can clearly see the phasor is rotating in the clockwise direction, and the period has increased because we have reduced the frequency. So, now the frequency is minus 2. So, the rotation direction has changed, okay, and let us say we set it to minus 7. Once again, you can see that it is rotating in the clockwise direction, but you still see the same cosine wave. The cosine wave is independent of the sign of the frequency because cos theta is equal to cos minus theta, but what the phase shift you can observe in the sine plot, okay, and the magnitude is still the same. But if you remember what happened to the phase earlier when it was positive, the slope of this sawtooth kind of shape was in the other direction for positive frequency, but for negative frequency you can see that the slope of this phase is now in the negative direction. So, observe this, the sine here, the sine theta starts from 0, and then for positive values of time it is reducing, which means it is minus sine theta or minus sine omega t, because we have negative frequency here, and the phase here has a slope. The sawtooth waves have a slope which is negative. Just look at this, and then now this is for positive frequency. Now observe that the phase plot has positive phases. So, the direction of the phase plot has changed, and if you look at the sine curve, which is the imaginary part, now this is sine, but it has at 0 it starts increasing. So, it is sine omega t, not minus sine omega t. So, the magnitude part remains the same for both the cases because the magnitude does not change. The phase is the only thing that changes, that we can clearly see in the phase plot, and the real value does not change, that remains the same, only the imaginary value changes, and that is also clearly observable in this. So, this is a complex sinusoid. We cannot represent that with a single plot, we need multiple plots. So, if you have a single plot, then you will get a polar plot like this, which represents the angle and the magnitude, but at only one time instant. So, if you want to observe this over multiple time instants, you either need the real part separately and imaginary part separately, or the magnitude plot separately and the phase plot separately. Okay. Now, let us change the magnitude and then see what happens, maybe 3. As you can see, the phasor size has increased, magnitude plot has changed, and the cos theta, sin theta, the real part and imaginary part, their amplitudes have changed, but the phase remains the same, right. The phase does not get affected with magnitude, that is also clearly observed here. Now, let us take a decaying or growing sinusoid and then observe this. So, if you remember what is a decaying sinusoid, it is nothing but the magnitude is not constant, but the magnitude is e power minus at. So, the a value here is minus 1 so it is e power minus t, so it decays with time. So in this case what happens, it starts at a very high value and starts decaying, and this is the magnitude plot that we have here. The magnitude is e power minus t, and that is exactly what we are seeing here. The phase is just e power minus t times e power j omega t, right. So the phase still remains the same, so you can still see the same phase, and the real part and imaginary part clearly show a cosine signal that is decaying and a sine signal that is decaying. So the real part is actually a cosine signal multiplied with e power minus t. You can see that at 0 it is getting a non-zero value, so it is a cosine signal, but it is getting a decayed value with time. Similarly, the imaginary part is actually a sine signal. You can see that at 0 it is 0, but only thing is, as time progresses the amplitude keeps reducing because the magnitude of the phasor here is e power minus t. Observe the rotation of the phasor. As the phasor rotates, this has a positive frequency, it rotates in the anti-clockwise direction, and as it rotates the magnitude becomes smaller in this polar plot. So this is an example of a decaying phasor. Now let us see an example of a growing phasor. All we have to do is change the sign of the exponent. So e power minus t is what we had, so we will just make it e power t and then observe what happens. So now we have a growing sinusoid. So this sinusoid grows beyond 1 for positive values of time. So as you can see here, the magnitude plot shows e power t, it just keeps growing up. Once again the phase remains the same because none of this affects the phase, we are changing only the magnitude. And as you can see, the real part and imaginary parts are once again nothing but real sinusoids multiplied with e power at, so they keep growing. So let us observe the rotation of the phasor. As you can see, as the phasor rotates with time, its amplitude or rather its magnitude keeps increasing. So it starts with a smaller magnitude phasor and then increases exponentially in size. So this is what we call as a growing phasor. Okay. So we saw growing phasor, we saw decaying phasor, and we saw constant magnitude phasor, which we call as the complex sinusoid. So once again you can play with the code here, change the frequency, change the amplitude, change the magnitude, and then see what happens. Okay. Play with it and observe how a phasor works. You can see the real part separately, imaginary part separately. It is very important to understand phasors because this course depends upon representing signals using phasors. Okay. Now what happens when you add two phasors? Once again, this is a very important concept and comes in handy later. So here what are we doing? We are adding three different phasors, okay, and phasor 1 has magnitude 1.5 and frequency plus 5, and another phasor has magnitude 0.7 and has a frequency minus 10, and the final phasor has a magnitude 0.4 and has a frequency 15. So if you see in this plot, there are three different crosses. So the phasor with magnitude 1.5 is the largest arm. On top of it there is another phasor which has magnitude 0.7, and then on top of it there is another phasor with magnitude 0.4. So there are three phasors which are added. So remember what we discussed about adding of phasors. So each phasor is put on top of the previous phasor. So the largest arm, as you can see here, moves in the anti-clockwise direction because the frequency is positive. Whereas the next arm, the arm with the magnitude 0.7, if you observe closely, it moves in the clockwise direction because its frequency is negative. Observe closely what happens, it moves in the clockwise direction. So the individual phasors here are moving or rotating in different directions. It is not necessary all should rotate in the same direction. Okay. So there are different phasors here all added up together, but they are all rotating in different directions with different frequencies. And then when they are all summed up together, we see the real part here of the sum, the imaginary part here, the magnitude part here, and the phase here. Now this is interesting because the real part and the imaginary part seem to appear periodic. Now are they actually periodic? We can answer this question from whatever we learnt. We have added three signals, each of angular frequency 5, minus 10 and 15. can this sum be a periodic signal? It is a periodic signal because if you take the ratio of the individual periods, it is always a rational number here, because the period of the first phasor is 2 pi by 5, the next one is 2 pi by minus 10, and the next one is 2 pi by 15. So, when you take the ratio of any two of these, you get a rational number because anyway pi gets cancelled out. So, because all of these are anyway turning out to have a ratio of a rational number, here we end up getting a periodic signal. Okay. So, as you can observe here, the phase is periodic, the magnitude is periodic, the imaginary part is periodic, and the real part is periodic. So, we have added up signals such that we have the ratio of their individual periods to be a rational number, and we got a periodic signal. Now, let us see what happens if we change one of the signal such that its time period is not rational anymore. So, let us modify one of them to contain a frequency which has, let us say, two pi. So, clearly as you can see, the magnitude is not periodic. It looks like a sine wave, but then if you observe the amplitude keeps changing in every cycle. So, this is not periodic. The magnitude plot clearly shows that it is not periodic. The real part also shows clearly that it is not periodic. It has a weird waveform, and the imaginary part also shows that it is not periodic. So, the moment even if one of the additive phasors have a frequency such that if you take the ratio of two different sinusoids there or two different signals here, the ratio is not a rational number, you can see that it is becoming aperiodic, or this is exactly what we studied, and that is what we are observing here. So, when you add signals, if they are periodic and their periods have a ratio of a rational number, then you get a periodic signal. So, this is a nice interpretation of how we can see multiple phases being added together, and we observe. So, if you see the real part and imaginary part, it looks like a random signal, right, but actually it turns out to be just three different phases added together, and the magnitude of the individual phases are all fixed, but if you see the magnitude plot of the sum of them, it keeps fluctuating. So, this is a very important idea which we will exploit later when we talk about Fourier transforms. So, make sure that you understand the addition of phasors. So, once again you can play with the magnitudes here, you can change the frequencies, you can increase more components or you can decrease components, observe what happens to these phasors when you add them or when you subtract them. So, if you just, in this case they are all added up together, if you want to subtract, you can just here change the sign and then see what happens when you subtract them. Okay. So, see what happens, observe what happens, play with it a little more till you understand. Okay. Then we have something about observing the symmetry of signals. Okay. So, this is our standard signal that we kept using often. Now, this looks like an asymmetric signal, and the second plot here plots the even component of the signal, the third one plots the odd component. As you can see, the even is symmetric about the t equal to 0 line, and the odd is a reflection about the origin. Okay. So, when you add these two, you get the original signal back. Now, what if we see something else? So, this is the step function. The step function has an even part which is given by just a straight line, and the odd part which is given by this sine function scaled, okay, the sinum function which is scaled. So, let us see what happens to the cosine part. So, once again the cosine signal is already even, So you see only the even part here, the odd part is all 0, okay. And the rectangular, once again the rectangular signal is already even, so the even part alone is non-zero, the odd part is completely 0. So let us see what happens to the symmetry when you time shift and scale them. So what we have done here is we have just here copied this part and then pasted here for the x of t, and this is x of minus t here. And then now we have a rectangular signal which is time scaled by just 1, which means there is no scaling, and we have shifted by 1. As you can see, the rectangular signal has moved to the left, but now the moment it is shifted, the symmetry is lost. Now you can clearly see that there is an odd component and there is a non-zero even component. Earlier it was a purely even signal, but the moment you shift it, it loses the symmetry. Now let us say that we are not going to shift it but only time scale it. So only time scaling does not change the symmetry. As you can see here, the signal is squished, there is no change in symmetry. Now we will expand the signal. Signal is expanded, once again there is no change in symmetry. We can observe this for other signals also. See here, this is already an asymmetric signal, so changing the signal anyway does not change the symmetry. Let us see, we take the cosine. So here the signal is once again shifted by 0 but scaled by minus 0.7. There is still symmetry that is remaining. At the moment we shift it, let us say we shift it by 1. Okay, we have shifted this signal exactly by its period, and so it still remains to be symmetric. So this is a very nice observation, right? So if you are shifting the signal exactly by its period, so here we have generated a sinusoid of period 1 and then we have shifted it by its period, so it still turns out to be exactly the same signal. Now we will shift it by a different amount. Now the moment you shift it by a different amount, whatever was even became an odd. Now let us shift it by something else. Now we have both even component and odd component. So this is a very nice example. So what we have taken here is a sinusoid, and we saw that when there is no shift, there was only scaling, there was no change in symmetry. Then we started shifting it. When we shifted it exactly by its period, once again there was no change in symmetry, and then we shifted it by half of its period, it became a completely different symmetry. An even symmetry became an odd symmetry. Now when you shift it by some arbitrary amount, it can now exhibit complete asymmetry. So this is a signal which we are able to get even symmetry by some appropriate shift, odd symmetry by a different shift, and complete asymmetry by a different shift. So this is a very nice observation that we can see, especially in sinusoidal periodic signals. Once again, play with different things here, see what happens, change the shift, change the scale, change the signal, and then see what happens to the symmetry when you change the scaling parameter, when you change the shifting parameter, and observe and play with this and understand what is going on. Now we will see what happens when we add two signals. Okay. Now we have two signals here, both are rectangular and they have individual energy 1. So when you add them up, you get a signal which has a higher amplitude and hence the energy increases, and when you take the product here, you get exactly the same signal and the energy remains the same. Now what if you change the amplitude of one of them? So the energy has increased both in the product and in the additive signal. Now let us change this to, let us say, a rectangular and a cosine signal. Now this is interesting, right? So you have a rectangular signal and a cosine signal, but once again the cosine signal has infinite energy, but we are plotting it only in the finite time duration. So the energy number denoted here is for this finite duration, but actually it is of infinite energy. So the additive term has an energy which is 11.33. As you can see here, the energies do not add up so the individual energy was 1 and 6.49, but they are not adding up when you just add these two signals. Anyway, cosine is infinite maybe, so let us take another signal. Okay. So, now we have a finite energy signal, both rectangular and the other signal that we have finite energy. So, each one of them have individually energy 1 and 5.33, but when you add them up together, the energy is 9.84, which is not the additive energies of one another, right. And when you multiply, once again the energies do not simply get multiplied together. So, this is what you have to keep in mind, and we observe that clearly from this. But remember what we said, if the signals were orthogonal, then they will end up having their energies completely added up together. Let us see if that happens. Let us take a rectangular function and another rectangular function probably, but now let us shift it so that it becomes orthogonal. Let us try and shift it. Okay. So, now we have a rectangular signal here, another rectangular signal here, both are orthogonal because they are non-overlapping in time, and when you add them together you see that the energy is also getting added up. This 0 1 is just an approximation error. So, we have energy 1 and 4 individually, when you add them together you are getting 5, and when you take a product it is 0. It is expected because they are non-overlapping, and you take the product it is 0. So, this also confirms what we saw, that if the signals are orthogonal and you add them up, the energies will also add up. So, let us see, take a sine wave and a cosine wave. Let us change their frequencies. Now, we have a sine wave here and a cosine wave here of different frequencies. Obviously, they are going to be orthogonal, but here anyway we are observing it for a finite window, so it does not really matter. We have to compute the power and not the energy here, because anyway individually they are all power signals. So, if you compute the power here, take this as an exercise, compute the power here instead of the energy, and you will see that they will add up. Okay. So, the energy of the cosine signals here is computed in the finite duration, but that does not reflect the actual energy because their actual energy is infinity. You have to compute the power. So, take this MATLAB code, add computation of power to it, and that will be an exercise, and if you can do that, it means that you have understood what is going on and how to work with the signals. So, take this MATLAB code and try and implement your own power function, play with different signals, change the frequency, their time, scaling and shifting, and observe what happens to this symmetry, what happens to the energy, what happens to the power and other properties of the signal.